Hello everybody, my name is Muhammad Amir Irfan Bisapari and my matrix number is 200681. So today I want to present about the dimensional analysis. A typical fluid mechanics problem in which experimentation is required consider the steady flow of an incompressible Newtonian fluid through a long, smooth-walled horizontal circular pipe. An important characteristic of this system, which would be of interest to an engineer designing a pipeline, is the force drag per unit length that develops along the pipe as a result of a friction. So the equation is force drag with four different independent variables, which uh, which is which are diameter, viscosity, density, and also velocity. To perform the experiments in a meaningful and systematic manner, it will be necessary to change the variables such as the velocity, which holding all the constant and measure the corresponding pressure. So when we do the experiment, well, we might use a lot of different value of the variable. So if we use 10 different velocity, 10 different diameter, 10 different viscosity and 10 different density, it will be about 100 graph when we done the experiment. So there's a lot of graph and it consumes a lot of time. So fortunately there is a approach to solve this problem while using dimensional analysis. So what is a dimensional analysis? Dimensional analysis is a means of simplifying a physical problem by appealing to a dimensional homogeneity to reduce the number of relevant variables. It is particularly useful for presenting and interpreting experimental data, attacking problems not amenable to a direct theoretical solution, checking equations, establishing the relative important physical phenomena, and also physical modeling. So we need to know about the dimension first. Dimension is a type of physical quantity. Unit is assigning a numerical value to that quantity. So the table that I put here is about the dimension and also the unit. So for example, the velocity have the unit ms negative 1, which dimension is lt negative 1. So formal procedure for dimensional analysis. Dimensional and dimensional homogeneity. The principle of dimensional homogeneity. All additive terms in physical equation must have the same dimensions. For example, the second formula for motion is S equal to ut plus half times at squared. So all the dimension in this formula have length n. So dimensional homogeneity useful for checking formula. So to do the dimensional analysis, we use a Buckingham's pi theorem. So these are the steps. So the first step is select pertinent variables. Second is write the functional relation, and third is select repeating variable. So for selecting the repeating variable, there are rules that we need to follow. First is don't select dependent variables. Dependent variables is is a force drag here, and second is variable should contain all the m dimension, which is mass, length, and also times. Do not select dimensionless variables as repeating. So first step is the number of pi parameters are n minus m. Write the pi terms by combining the repeating variable with each of the remaining variables. Solve the equation from step 5, and the last one is write the functional relationship pi equal to functional pi 2, pi 3, and etc. So the first step is partial variable. So in this equation, we have 5 variable, which is force drag, diameter, viscosity, density, and also velocity. So n equal to 5. So the second step is write the functional relationship relation. So this is so here. So select repeating variables. First, before we select the repeating variables, so we need to know how many m we have. So in this equation, we have so the m is independent dimension, which is mass, length, and also times. So we check in this equation. So the diameter, the dimension is length. Dimension for viscosity is m l minus 1 t minus 1, and dimension for density is m l negative 3, and dimension for velocity is lt minus 1. So there's a 3 independent dimension, which is mass, length, and also time. So now we need to select the repeating variables. So first rules, don't select the dependent variables, which mean we do not take first drag as our repeating variables. Okay, so the second rule is variable should contain all the m dimensions mlt. So all of these variables have m and mlt. So I choose density, velocity, and also diameter. So in here, density have all of them have L. So in this have T, which in velocity, and also in this also have M, which in the density. So the third rule is do not select dimensionless variables as repeating. So there is no dimensionless variables in this equation. So the fourth step, the number of pi parameters are n minus m. So n is 5, m is 3, so n minus m is 5 minus 3 equal to 2. So there is two important dimensionless parameters which will characterize this problem. So the fourth step, the fifth step, this is the fifth step. So we choose three independent variables. The fifth step is write the pi term by combining the repeated variable with each of the remaining variables. So we have so I choose density, velocity, and also the diameter. So and for pi 1, so pi 2 is also the same. That's why we call repeating variables. We use the same variable. We use the same variables and repeat them for each parameter. So there is two remaining variable, which is force drag and also viscosity. So we take them in the first pi and viscosity in the second pi. So we put the dimension for the variable. So density is m over l cube. Velocity is l over t power to the power of p, and diameter is l to the power of c. And force drag force is m l over t cube. So same for the pi 2 second pi is m over l cube to the power of a to the power of a, l over t to the power of b, l to the power of c, and for the mu, which is viscosity, m over l times t. So we solve we get that, and we solve in the sixth step. We solve the step in step 5. So after we solve this and we get the algebra. So after solve all the algebra, we get a equal to -1, b equal to -2, c equal to 2. So we put back the value that we get into this. So density equal to density to the power of -1, velocity to the power of -2, diameter to the power of -2 times ft. So we rearrange this, we get this ft over density times v squared d squared. So same as second pi, we use the same way. We get the algebra and we get the value of a and b and c. Oh, so I forgot to mention that a plus 1 equal to 0, -3, a plus b plus c plus 1 equal to 0, -b equal -2 is equal to 0. Why all of them is equal to 0? Because all of this is a dimensionless. So we can prove that all of this is dimensionless by doing it ourselves. So that's why all of them is equal to 0. So after solve the second part, we get mu over density times v times d. So when we plot the graph, we use pi 1 versus pi 2. So instead of we get 100 graph, we only have one graph. So whatever velocity, density, viscosity, and density, we use all the data we fall on the single line. So this is a single line. So whatever data that you use, and whatever value that you use for the velocity and all of that, we only all of the data will fall only on a single line. So from this equation we get this equation. So drag force was a function of 4 different variables. So when we use the dimensional analysis, we end up get a drag coefficient is with only one variable, which we have which will be a lot easier for us and to get the data and to plot the graph. So that's all from me. Thank you.